Hello, welcome to the notes for chapter 4. We are going to start today with section 4.1, Extrema on an interval. The objectives are going to be discussing what extrema are, comparing relative extrema with absolute extrema. We will then see the second theorem of AP Calculus AB, the extreme value theorem, abbreviated EVT, and then we will study examples of how to find extrema on a closed interval. So first we'll discuss what a maximum is, and the maximum is the value of a function f such that it is greater than any other output for the domain. So on a sketch, on a graph, it's the highest point. When we say maximum, when we say the maximum, we typically mean the absolute maximum, so the highest of all. Then there's an equivalent definition for the minimum, so the lowest point on a function, on the graph of a function, and it's the y value, which is that is the minimum. And now an extremum is the combination of both. So sometimes instead of saying find the maxima and minima, we will just say find the extrema. And there's another term to say that, it's extreme values. So in the example here, we have the function f of x equals x squared, which we all know how to graph. If we are looking for the extrema of this function, we are looking for the highest point and the lowest point. The minimum is y equals 0. This is as low as it gets. And now for the maximum, there is no maximum because we can always go higher. Notice that to answer the question what is the minimum here, the minimum is y equals 0. So I want to draw your attention to this little double line here. When the question is what is the max, your answer should be the max is y equal. If the question on the other hand asks where is the max, then your answer should be the max is at x equals something. This is quite an important detail. You don't want to be answering the wrong question and giving an x answer if we're actually expecting a y answer, or vice versa. Question B, find the extrema. So again, find the max and the min on the interval from -1 to 2. This is a closed interval because it's like square brackets. So it means we have a graph like this. Now the minimum, or absolute minimum, is still going to be y equals 0. The maximum, however, now exists. Because we've limited the domain, we have the maximum of the function here, it's y equals 4. So the full answer for this question is the absolute max is y equals 4, the absolute min is y equals 0. The parenthesis here is additional information, but they would not be required since the question is simply find the maximum, find the minimum, not where is the maximum, where is the minimum. What can be said of the extrema on this function given that interval? Notice that here we have these curved parentheses, so this is an open interval which corresponds to having holes in the end. And there is no minimum and no maximum. There is no point that I can show on the graph that is the highest of all. I can always go a little bit higher, a little bit higher, a little bit higher, and I will never reach the last point. We've talked about absolute maxima and absolute minima. The alternative is that you could have local maxima, local minima, which are also called relative maxima, relative minima. So what is a local maximum? It's a point, like this one here, that is higher than every point near it. So you can see this is, if you couldn't see very far, you would think this is the absolute maximum. Actually, there are points elsewhere that go even higher. But if you only look at a small neighborhood, it can be very, very small, in fact. But if it's the highest point in its neighborhood, then it's a relative max. On this graph here, you can see that you have a relative min here and another point down there, which is the absolute min. When you are absolute min, you are also relative min. So absolute min is like an extra medal that you earn. Of course, this point is a relative min because if you focus on the neighborhood, it is the lowest of all, so it's the relative min. But on top of being a relative min, it is the absolute min. There are no absolute maxima on this graph because the graph goes up to infinity, so there is no highest y value. So if we want to compare relative max with absolute max, you can think of the Himalayas. It has lots of mountains. Each mountain is a relative max, but only Mount Everest is an absolute max. So in chapter 3, we talked about the IVT. Today we will see the EVT, and this is connected, as its name says, extreme value theorem. It is connected to absolute max and absolute min. Let's read it. If f is continuous on a closed interval, then f has both an absolute maximum and an absolute minimum value on the closed interval between a and b. So what this says is we are in a situation like a little earlier, let me go back up, like this here, where we have a function that is continuous, so there's no jump, there's no asymptotes, there's no holes, and we have a closed interval. So in this example, we started at -1 and we ended at 2, and the endpoints were included. So we have these square brackets. In a situation like that, there will always be a maximum and there will always be a minimum. By that I mean there will always be an absolute maximum and there will always be an absolute minimum. These values that we may be looking for can only happen in 3 places. These are what I call the candidates. When I'm looking for an absolute max or an absolute min, I'm going to list all the candidates and then just simply check which one is the highest. So what are the places where the absolute max and absolute min can hide? The first one is we can find absolute mins and absolute maxes where the derivative is 0. It would look like this. We would have a horizontal tangent. We know that that corresponds to f prime equals 0. And this could be the absolute maximum of the function on the closed interval. Another possibility for a maximum to appear is if you have, for example, a sharp turn. So this is up here the absolute max of this function, at least a portion of the function I see. But you can notice that f prime is not 0 here. So sometimes when f prime is undefined, it can correspond to an absolute max or absolute min. So we should always look for places where f prime is undefined because maybe the maximum is hiding there. Finally, the last possibility is that the absolute max is at one of the endpoints. So in this example here, the function is growing and growing, and in the end, the highest point on the graph is the endpoint. So if we look at the example above, what happened is the absolute max was indeed at an endpoint. The absolute min was at a place where f prime of x was equal to 0. So in this example, there were no situation like number 2 here. We had an absolute min at the situation number 1, f prime equals 0, and we had an absolute max at situation number 3. It was the endpoint on the right. These sketches show absolute max values, but of course you could do similar sketches for absolute min values. So we do exactly the same process to find the absolute maximum and the absolute minimum. Out of these 3, the first 2 have a special name. When you find the x value where these characteristics happen here, these are called critical numbers. So in a place where f prime of c equals 0, or a place where f prime of c is undefined, we say that c is a critical number. So it corresponds to number 1 and number 2. So the endpoints are not critical numbers, but if we pair critical numbers and endpoints, That's how we find all our candidates for extrema on a closed interval. If there's an open interval, then line number 3 doesn't exist. There's no endpoint. But of course, if it's an open interval, we also cannot use the EVT because the EVT requires a closed interval. Let's see two examples to maybe help us make a little bit more sense of that. There's a graph at the bottom, but maybe we want to pretend it's not there to start with. So here's a function y equals x to the power of 2 over 3, and it might not be obvious at all what this function looks like. If you're completely lost and you want to make a sketch, then the best way is to make a table of values and see what it looks like. But we are going to proceed in a very formatted way to find the extrema. We know where the candidates can show up, number 1, number 2, number 3, so we are going to look at each of these possibilities one after the other. For 1 and 2, we need the derivative. So firstly, let's calculate what the derivative is. F prime of x equals 2 over 3 x to the power of negative 1 over 3. If I rewrite that, it is 2 over 3 times the cube root of x. So, first possibility, f prime of x equals 0. Would that ever happen? No. I would need the numerator to be 0, and that obviously is not the case. Second situation, f prime of x undefined. Could that ever happen? Yes. If x equals 0, now the denominator will be 0, and f prime will be undefined. So I have found one candidate. Finally, the endpoints. And the endpoints are always given, and here we are going on the interval from negative 2 to 3, so negative 2 and 3 are the two endpoints. That means I have three candidates. I have x equals negative 2, x equals 0, and x equals 3 if I put them in order. In order to find which one is the absolute max, it's quite easy. I know it's one of these three, so all I need to do is to calculate the value of y, and then I can just compare them and see which one is the absolute max and which one is the absolute min. So plug in x equals negative 2, make sure that you plug it in the function itself, because we are looking for y, not y prime. We get that y equals the cube root of 4, for x equals 0, y equals 0, and for x equals 3, y equals the cube root of 9. Therefore, just by comparing these three values, we can see that 0 is the smallest of all, so it's the absolute min. And we can see that the cube root of 9, even though we don't know exactly what it's equal to, but it's definitely greater than the cube root of 4, so it's the absolute max. Finally, what about cube root of 4? We would not have to write anything necessarily, but just thinking logically, if at 3 we are at the highest point, and 0 we are at the lowest point, then to go to x equals negative 2, we must have been going up again, and that means this has to be a relative max. So, we don't have to state x equals negative 2 because it was not asked where are the extreme values, simply what are the extreme values. The second example is exactly the same question. Well, it's not exactly the same question, but it's a similar question. We're going to be looking for the critical values. However, we have a piecewise function, so we have to be careful. So the question is not the same. We are not asked what is the max or min. We are asked what are the critical values. So in fact, if I slide back up, we are now just asking the x values for option 1 and option 2. We are not wondering about the y values in this case. But the idea is similar. We want to find the derivative and then set up f prime of x equals 0 and f prime of x undefined. You can see that I put number 3 in parentheses because it is doubly irrelevant. Firstly, it's irrelevant because it's not even a closed interval, so there's no endpoint. And secondly, it's irrelevant because it's not a critical value. The endpoints are not part of the critical values. So, the derivative for a piecewise function, you just take each rule and differentiate it separately. So the derivative of x cubed minus x would be 3x squared minus 1, and the derivative of x is 1. There is one difference though. There was an equal sign here, and it's gone. So why is it gone? And can we ever carry it over from here to there? Maybe, maybe not. You have to check. Because here there's a weird junction. We might have a jump, or we might have a sharp turn here. So we have to check that our one-sided derivatives are equal in order for f prime to be defined at x equals 0. So first of all, we may wonder, is the function continuous? Because if the function is not continuous, obviously there's no derivative. And to check if it's continuous, I would plug in x equals 0 here. I would get 0, and I would also get 0. So the function is continuous. Is it smooth at that point x equals 0? The left-sided derivative tells me that the slope from the left is equal to 3 times 0 minus 1 equals negative 1. On the other hand, the right-sided derivative is positive 1. So there is a sharp turn. The slope is negative 1 from the left, positive 1 from the right. If there's a sharp turn, it means that f prime of 0 is undefined. So I'm not allowed to put equal because there is no derivative for x equals 0. Okay, so that was a detail, but it can be consequential. It's very technical though. So first option for critical points, f prime of x equals 0. Let's look at the first rule. It means 3x squared minus 1 equals 0. We solve and we get x equals plus or minus square root of 1/3. We can only accept the answer x equals negative square root of 1/3 because that rule only applies for negative values of x. So x equals plus square root of 1/3 is irrelevant. What about the second rule? Can 1 ever be equal to 0? Well, no, obviously no, it's a constant. Okay, so we can go to the second option, f prime of x undefined. Now we have already found a place where f prime of x is undefined because we have noticed that when x equals 0, the one-sided derivatives are different. So x equals 0 is a critical value and we should not forget it. Now, are there any other places where f prime of x is undefined? 3x squared minus 1 is a polynomial, so it's always going to be defined. And the derivatives, successive derivatives of polynomials are always defined as well. And of course, 1 is always defined, so there's no other critical value here. We have talked about why the endpoints are irrelevant. It's not a critical value, so we shouldn't even have to talk about that. But moreover, we don't have a closed interval here, so there would be no endpoints. In conclusion, the critical values are x equals negative square root of 1/3 and 0. A note, this is the graph that the function looks like. And so if the question had been find relative maxima and relative minima, we would have found a y value here. It would have given us a relative max. And this point here, y equals 0, would be a relative min. In its neighborhood, it's the lowest point. And it appears from the graph that there are no absolute max and absolute min because this line y equals x goes on forever. And on the other side, the cubic function y equals x cubed minus x will just go down forever. So that's it for this section. Thank you very much for listening.